Assalamu alaikum dear students. In this lecture we are going to learn the fundamental theorem of calculus, and which is very important theorem in entitled calculus, and it actually gives the relation between the integration and derivatives. It allows us to evaluate different integrals in an easy way, and what else it can do and what are the advantages of it. Let's see. So first advantage, as I told you, it gives the connection between the integration and derivatives. It computes integrals using antiderivatives of the integrand functions. So we have no more rectangles, we have no more Riemann sums in order to evaluate the definite integrals. So it makes our life easier in order to finding the values of definite integrals. So you can see it gives the connection between the integration and derivatives. Although we are studying integral calculus right now, but without derivatives, the concept of integration is incomplete. So we cannot go away from the concept of derivative at all. Okay, the section summary. So what we are going to do and what is in store for us in this section. First of all, we learn the mean value theorem for different integrals. You would have seen the mean value theorem in last course as well. That was about derivatives, and this is the mean value theorem for different integrals. And then we have fundamental theorem part 1, fundamental theorem of calculus part 1, and then fundamental theorem of calculus part 2, and then the applications of these theorems to find the net change in the function, or to find the areas under the curve. So let's begin with the mean value theorem for definite integrals. Now, if f is continuous, the statement of the mean value theorem is if f is continuous on closed interval, then at some point c in the closed interval, the function f attains its average value. Okay, so here is the function which is continuous on the closed interval ab. So there must exist some point where height of the function is its average height, is equal to its average height. So let's see how can we prove this. We'll prove this with the help of maximum minimum inequality. So according to maximum minimum inequality, and we discussed it in the last lecture in detail, the value of this definite integral lies between the maximum value multiplied by b minus a and the minimum value of the function multiplied by b minus a. Now, since b minus a is positive, because this is the length of this interval, so we can divide the whole inequality by b minus a without altering the inequality. So we have this result. Now, what does this mean? This average value lies between maximum value and minimum value. Now, if a function is continuous, again, function is continuous, function has a maximum value and minimum value, then according to intermediate value theorem, um, uh, uh, and which you learned in calculus 1. Yes, there are so many results we are using from calculus 1 in this calculus part 2. So from intermediate theorem, value theorem, the continuous function says that f must assume every value between minimum and maximum value. Okay. Now, since average value lies between maximum and minimum value, so f must attain the average value as well. Okay, so there is a point C in the enclosed interval such that fc is equal to the average value of the function. So this proof completes the proof. Okay, now the condition of continuity is very important. So whenever you are going to apply this theorem, make sure that your function is continuous, because if function is continuous, this condition might not be possible. Okay, so this is not true, may or may not be true for discontinuous functions. For example, if we have a function defined here, which is discontinuous function, it has term discontinuity at x is equal to 1. This is defined in the interval 0 to 1. So from 0 to 1, value of the function is 1. From 1 to 2, value of the function is 2. And the average value of the function, is 1. 1, and this is 0. So value of the function is 1 by 2. Adding these 2 and divided by 2. So we have the value of the function is 2. Okay, but this function does not assume the average value in the whole interval. So the condition of continuity is a must. So this continuous function need not assume its average value. Okay, show that next example of the application of mean value theorem. Show that if f is continuous on the closed interval ab where a is not equal to b, and if integral from a to b fx dx is equal to 0, then fx is equal to 0 at least once in the interval ab. Okay, so let's find the average value, then we'll conclude something. So average value of the function is integral from a to b fx dx divided by b minus. Now this integral is 0. This is given. So this is 1 over b minus 1 multiplied by 0. This is 0. So average value of the function is 0. Now according to mean value theorem, since f is continuous on the closed interval ab, so according to mean value theorem of integrals, function must attain average value in the interval. Okay. So average value is 0. So according to this theorem, there is some point C where FC is equal to 0. So this is where we have to, at least some point, at least one point C where FC is equal to 0. Oh, now the fundamental theorem of calculus part 1. Fundamental theorem part calculus part 1 states that if f is continuous on closed interval AB, then fx, the upper case fx is equal to integral from a to x f dt is continuous on the closed interval AB and differentiable on the open interval AB, and its derivative is defined by this. So this is what we have to prove. Okay, derivative of this integral is equal to value of this function at x. Okay, this is what we need to prove, and what is given, f is continuous and fx is equal to this integral. This is given. Now, what does this integral represent? Now, this is the function, graph of the function, which is defined in the closed interval A. Now, x is any point inside the interval A. So, instead of finding the area from A in the closed interval AB and the curve, we are going to find or going to describe this area over the closed interval ax by this integral from a to x f dt, and we say that this is fx. So this area is fx, okay, and this is the graph of f dy is equal to f. Now we have to differentiate this area. Area is function of x because x is variable. So area is function of x in this case. Area is variable. Now by the definition of the derivative, we know that a derivative of this function f dash x is defined by limit of f x plus h minus f x divided by h and h approaches to 0. So this is by definition derivative of this function. Okay. Now by plugging in the values, let's see what happens. So we have the definition given here. This is the definition of the derivative of this function. Now by plugging in the values, we have f of x plus, since f of x is given by integral from a to x, so just replace x by x plus h. So f of x plus h is integral from a to x plus h minus f of x divided by h as h approaches to 0. Now by interchanging the limits, we have plus x to a. So x to a plus a to x plus h, this gives us x to x plus h. So this is equal to limit h approaches to 0, 1 over h times integral of x to x plus h after dt. So we are left with this integral. And what does this represent actually? Now the point to ponder upon. What does this represent? This is an integral or area defined in the interval x plus h under this curve. Okay, so this defines this area. Alright. divided by h. H is actually the length of this interval. So what is this? This is the average value of the function, average value of the function in this interval x plus h. Okay. Now since function is continuous, so there must be some point c in the interval x plus h such that this average value is equal to, that is 1 over h integral x plus h ft dt must be equal to f of c, right? This with the help of mean value theorem we just learned. Okay. Now, what is this limit will be then? This can be written as here. F prime x is equal to this, and this can be written as fc. So limit as h approaches to 0, f of c is equal to, now what happens when h is approaching towards 0? When h is approaching towards 0, so a value of fx is approaching towards value of the function approaching towards fx. Okay, so value of the function approaching towards fx. So limit as h approaches to fc is equal to fx. So this is what we want to prove. The derivative of this function, this integral, is fx as required. This is the proof of this thing. Alright, in the application of this theorem, let's solve a few questions. First of all, we have y is equal to from 0 to x1 plus t square. So, what is the value of dy by dx? Question here is, what is the value of dy by dx? That is, what is the value of derivative of this function? Okay, so dy by dx is equal to d by dx of this integral. Now just compare it with the form a to x d derivative f t dt is fx. This is what we learned from fundamental theorem part 1. Now compare it with this. A here is 0, x here is x, ft here is 1 plus t square. So what should be the answer of this derivative? This must be equal to f of x, that is 1 plus x squared. Okay. Okay, next question. So we have this question again, same procedure. We have d by dx is equal to the derivative of this integral under t dt, and comparing with this, a here is 1, x here is x, ft here is 1 over t, so it must be equal to f of x, that is answer is 1 to x, where x is greater than 0, because at x is equal to 0 it is going to be undependent. Okay, next. Yes, this is a bit challenging question. So in order to find the derivative, we have two functions here, x multiplied by integral from 2 to x squared sine t cube dt. Okay, so we have two functions. One function is x, one is other function is this integral. So we will use product. Both the functions are multiplied with each other. So we are going to use product rule in order to find the derivative of this function. So let's start. Dy by dx in this case is, first of all, derivative of x and this integral as it is. That is 2 to x square sine e cube dt plus x as it is, derivative of 2 to x square sine t cube dt. Now compare it with this, this one. Okay, so there is some problem. Here we have x, here we have x squared. What we need to do? We have to transform into a variable like x, variable u, y, any other variable, but we don't need any non-linear part. We have to have x here or y here or u here. So let's make a substitution in order to solve this. Now this part is done. Now in order to solve this, just to solve, we get back to it. Let's solve this first. So to solve or to find the value of 2 to x square sine t cube dt, uh, let's make an assumption that x square be u. Okay, then this becomes dy dx. Okay, now we have d by dx. Then by making this assumption, we have 2 to u sine t cube dt. Now again compare it with, now you are going to differentiate this integral with respect to the variable here, okay? But in this case, where we are going to differentiate with respect to x, but variable here is u. So what you need to do, you have to apply the chain rule. So by chain rule, d by du, that is derivative with respect to u, 2 to u sine t cube dt, and multiplied by du by dx. So this is the chain. So let's plug in the values. So this is equal to, now we can use this theorem. So function here is ft, here is sine t cube. So this will become sine u cube multiplied by du by dx. So du by dx actually is 2x. So 2x. Okay. Now substitute backward substitution will give us u is equal to x squared, so plug this value into this. Sine x square cube is 6 into 2x. So you can write 2x here. So this is equal to 2x sine x cube. Okay. So what is the value of this now? So our dy by dx becomes dy by dx is equal to, we have 2 to x square sine t cube dt plus x dy dt of this is 2x sine x 6, or you can write it as 2 to x square sine t cube dt plus 2x square sine x 6. So this is how we can evaluate the derivative of the integral if our limit is different from x, any arbitrary function of x such. We can evaluate this derivative. Okay, fundamental theorem of calculus part 2. If f is continuous over the interval ab, then f is any antiderivative of f on ab, then integral from a to b fx is equal to fb minus fa. So there are two things to note. F is continuous on ab, so this is actually a must. And then this f, uppercase f, is antiderivative of this lowercase f. Then we have to prove. So this is given between f and n, and now we have to prove integral from a to b fx, this definite integral, is equal to fb, value of this antiderivative at b minus value of this antiderivative at a. Okay, let's do it. So Part 1 of the fundamental theorem tells us that any antiderivative of f exists. Namely, we just assume that antiderivative of f is gx is equal to integral from a to x f dt. Now, one of the antiderivatives is given in the statement, which is f. Now, if we have two antiderivatives of a function, in calculus 1 we learned that they differ by a constant. So fx is equal to gx plus c. Since f and g both are antiderivatives, so fx is equal to gx plus c for some constant c, and x lies between a and b, of course, because we have the function which is continuous in the closed interval a and b. So it is differentiable in a b. So since f g are continuous on a b, closed interval a b, then let's find the value. Then they are defined on a and b as x approaches to the values greater than through values greater than a, and as x goes to b through values less than a. So let's find the value of fb minus fa. So let's see what happens. Fb minus fa is equal to gb. We are just plugging these values into this relation. So fb minus fa is equal to gb minus gb plus c minus ga plus c. C is constant, so it doesn't make any difference. So we are left with gb minus gc, because positive c, negative c will make it 0. Now just plug in the values. Gb is equal to a to b f t dt, and ga is equal to a to a f t dt. Okay, so integral from a to a is 0, and we are left with integral from a to b f dt. So we have integral from a to b f dt is equal to fb minus fa, where f, this uppercase f, is antiderivative of f. So this completes the proof. Okay, this is actually immediate consequent of the fundamental theorem part 2 is that we can use this theorem to find the net change in the function. So net change in the function fx over an integral over the interval closed interval ab is the integral of its rate of change. Okay, so integral of its rate of change gives us the total change in the function. So if we you have to find the you have the velocity function, and you have to find the total distance. So you can use this net change theorem in order to find the distance covered. But you must have to be careful if there is some in some intervals the velocity is negative, or distance covered is sometimes mixed with the displacement. So this gives actually the displacement in general. So if I represent the rate of change of the function with respect to x, so this equation asserts that the integral of f is just net change in f at as x changes from a to b. Okay, now area problems. Area problems are a bit tricky problem, because we define that integral from a to b fx dx defines the area under the curve fx over the closed interval ab. Okay, but sometimes, okay, if the curve is like this, then this is really an ideal situation. There is no problem in it. This integral will give us the area. But if the our curve lies below axis, then what's going to happen? And there is a, there is b. So this will give us the negative of this area, because every value of y here is negative. Every value of the function in this interval is negative. So this will give us the negative value of this area. So if we are required to find the area, we have to take the absolute value of this integral, a to b fx, right? sometimes what happens? Sometimes a graph like this looks like this. This area is equal to this area. Now this is the positive value of this area, this is negative value of this area. And if we, and this is the point A and this is the point B, and when we evaluate the integral, it will give us 0. Okay, but area is not equal to 0. Area is the area over here, and this is the negative of the area, so this so area becomes 2a, right? So how to solve these problems? Let's have a look at this with the help of examples. So first example, this figure shows that uh, the graph of f in x is equal to x square minus 4. This is the graph of x square minus 4, and its mirror image is 4 minus x square. Now this graph lies below the x-axis. This graph lies above the x-axis. Now reflected across x-axis. So for each function, compute the definite integral over minus 2 to 2, and the area between the graph and the x-axis over minus 2 interval. Okay, first evaluate the integral. So for the function fx, integration is just an antiderivative, and you just have to find plug in the value. So antiderivative of fx here is fx is x squared plus 4, x cube over 3 minus 4x, and you know it very well. So by plugging in the limits a to b, there is minus 2 to 2. We have this is the actually implementation of fundamental theorem part 2. So by plugging in the limits, we have minus 32, negative 32. Now because f lies below x-axis, the value is negative, and the integral from minus 2 to 2 of the function gx, which lies above x-axis, is positive 32 over 3. So area covered by both the functions is same, but the value of this integral is negative because of the function. It lies below x-axis. That is why we have the negative value. Now, if we have to find the area, then we have to take the absolute value because area cannot be negative. So, in both the cases, area between the curve is over the interval minus 2 to is 32 over 3 square meters. Okay. So, uh, although definite integral is negative, but area is still positive. Area cannot be negative. Okay, if there is a situation like this, I told you before, then what to do? We have to find this area, and then we have to find this area separately, and then we'll add both the areas. Okay, if we integrate this, we have 0 from 0 to 2 pi. If you integrate this function, fx is equal to sin x, we have a 0 value. Okay, and if we have to find the area, then we'll have to split this positive part and the negative part. We'll calculate them separately, and then we'll add the positive values, ignoring the sign, that is absolute values. We're going to add absolute values of the integrals. So 0 to pi we have 2. So similarly pi to 2 pi we again have 2, but in negative sign. So area here is 2 plus absolute value is negative. This is 4. The total area is 4. So this is how we are going to solve area problems. So what is the summary of this procedure? So first of all, what we need to do, we just have to find the zeros of fx. So find the values where fx is equal to 0. And if those zeros, find those zeros which lie inside the interval A. So subdivide the interval, add zeros of x. Okay. And then integrate f over each interval, add the absolute values of the integrals, and then we have area. And so this is another example of the area where we can have negative value of the integral and positive value of the integral. So area can be formed first of all, the function here is x cube minus x square minus 2x. Okay, we have to find the area of the region between x-axis and the graph in the interval. Interval is given here -1 to. So find first of all, following the procedure, first of all find the zeros of f. Now zeros of x are x is equal to 0, -1 and 2. Now -1 is this endpoint, 2 is this endpoint, and 0 is in between. So we have to break this at 0, this interval at 0. So -1 to 0 we'll evaluate separate, and then we'll evaluate the integral from 0 to 2. Okay, so -1 to 0 we have this value, and 0 to 2 we have this value, which is negative. So area here is 5 by 12 plus absolute value of this negative value, and this is 7. This is how we are going to solve the area problems. And that's all for today's lecture. See you in next lecture with new topic. Take care. Till then, bye bye.